What we're going to do is we're going to take a look at this as an example, expand upon it. So the business model, first of all, that they had, from your reading, was that they had options, right? What were their options that they can make? What were the options? Fancy versus sport skateboard. Okay? Sporty, sorry. And the things that were important here for the business model was if they were glued and pressed, the shaping, the trucks themselves, and recognizing that we have some limitations to our resources. That's one of your constraints automatically. Now, the data that was presented in this was that the profit from these two types of skateboards was different, but the time it took was also different. So before you even read and before you began, you should have probably looked at this already and said to yourself, so I make more money on the fancy ones, but it takes triple the time. So right off the bat, you knew your answer should have been sporty, actually, because look, you don't make triple the money. What should this number be if it was triple 15? 45. Yeah, if this was 45 and 15, and this was 15 and 5, this is triple the time. If you make triple the money, then it's a break even, right? You see what I'm saying right off the bat? Without even optimization, without Excel, you should be able to see that logically. If this was a number like 80, right? To go from 15 to 80, you're making like 6 times the profit almost. Well, it only takes 3 times as long to make it. So it makes more sense to make the one that gives you 6 times as much profit if it only takes half as much, or not half as much, but 3 times as much time to make it instead of 6 times as much. So you can think about that already. The shaping time is something that you want to minimize, really, right? Shaping time needs to be under a certain value. Whereas the profit, what do you want to do with that? What do you want to do with the profit? Yeah, so what is the term for that? Increase. What's the term for that? Not minimize. Maximize. Come on, I just used the word minimize, right? I said you want to minimize the shaping time, so you want to maximize the profit you're making. So we have to start thinking about this. Now, you read this. What was your objective function? What was your objective function? What was the objective function? What's the overall thing you're trying to do here? And
Z equals 15x1 plus 35x2.
Yeah, he said z equals 15x1 plus 35x2. Well, what he's trying to optimize, or in this case, is the objective function here, is the profit function. You make $15 profit for the first type, that's 15x1. You make $35 profit for the second type, that's 35x2. Think back to your math course freshman year. If you wanted to see how much money you made in revenue by selling tickets, you did these problems all the time. It was 2 variables, 2 equations. You always did it with substitution method or elimination method in your math course. Sometimes if you use the matrix. So that's what your goal is here. You're trying to figure out what you can maximize, or what you have to maximize, which is profit. Your limiting factors, there's several limiting factors here, and we're going to keep adding more limiting factors as we go on, recognizing that it's more difficult to find the solution by hand, which is why you would then go to some sort of a solving algorithm. All right, so first, decision variables. Decision variables. What are the decision variables here? What are the decision variables? Sam?
Where X1 is the production rate of the sporty brands and X2 is
Fancy. That's exactly right. X1 and X2. Number of sporty brand, number of fancy brand. So right away your decision variables are X1 and X2. Now, Anthony already told us the second part, right? He told us, okay, you know what? If the sporty brand is X1 and the fancy brand is X2, well, we make $15 for every sporty one and $35 for every fancy one. So that's going to equal the total profit, which in math we actually call the objective function Z. Okay, I'm hoping you're all looking at what I'm looking at, right? Yes? Okay. You're intently looking at your computers like there could be something else going on. I really hope you're focusing. So this is your objective function that we're looking at here. Now, what about constraints? What about constraints? What do we have? Chris, what do you got? Time. So do you have an equation for a constraint in this case yet?
It was like the inequality was like it has to be less than 2,400.
It gave you a number, right? When you're reading through, it told you how many days and how many hours you can work in a week and the shaping time per board. How much time did it take to shape the sporty board? How much time to shape the sporty board? It was 5 minutes for the sporty board. How much time did it take to shape the fancy board? 15 minutes. And what did we want to stay under? We wanted to stay under a certain amount of time. How much time was that? 2,400 units? Minutes. Why did you have to convert to minutes? 40-hour work week, right? Why do we have to convert this to minutes? Why minutes? Sam, you had your hand up first. You know what? Help her out, Klaus.
Because like the production of each unit is measured in minutes.
Yes. This is measured in minutes, right? 5 minutes and 15 minutes. If these were like a half an hour and 1 hour, these units would be hours. Remember in physics you had the dimensions that to match up? Same thing here. These are measured in minutes each, 5 and 15 respectively. That has to be in minutes. So that's your inequality. Any other inequalities? Any other? Caroline?
Needs to be non-negative.
Non-negative. What does that mean, Caroline?
Means that x1 and x2 have to be above 0 or greater than 0.
Absolutely. You can't have a negative amount of produced items. You can't produce a negative amount of items, pretty much. So those are your non-negativity constraints. That occurs a lot, non-negative constraints, actually. And when you go to Excel, what's cool, I think there's a feature, if I recall correctly, that all you have to do is check a box. And it makes sure that all of your decision variables cannot be negative. You don't have to set up all the constraints for every decision variable. Because how many decision variables do we have here, guys? How many? Two. In real life, there's like thousands in one problem. When you think about airlines and when there's a cancellation in a flight, have you ever been frustrated by that? Well, they have a linear optimization program running with like 30 million decision variables. Those decision variables are absurd, and they have to optimize them all. So as a result, you can't have like a program that you have to enter every constraint. So you have a non-negative constraint in general. Okay? Simplifies things for you. All right. So we have this already. I'm just going to fly through this because this is what we were talking about. Okay, x1 and x2 are our decision variables. We want to maximize our profit. If you confused you on the last one, it's $15 per sporty times the number of sporties. Well, what happens? What happens to the unit of sporty, which is a weird word to say? Yeah, they cancel out. Go back to physics. Cancel out. What are you left with? You're left with dollars. Dollars and dollars. So this equation is all about profit, or dollars. Those are the units for this equation. For this next one here, we obviously know that this is time. This is 5 minutes per sporty times the number of sporties. Again, canceling. Fancy, canceling. Leaving you with minutes, minutes, and minutes. The same units for all three. Does this make sense so far? Yes? No? Maybe so? I need to know if this is confusing, because it's going to get more confusing as we go through, or more, not more confusing, but it's going to get more detailed, okay, as we go through. And then finally, the non-negative constraints here at the bottom. So this is our overall summary that we were looking at a moment ago. So we want to maximize one thing subject to three constraints. So now that we did Excel, let's jump to the next constraint. Now, what we can do is look at this next actual inequality we're seeing here. What does this inequality look like to you? Where did that come from? Any idea? Any idea where that inequality came from? I know it's an inequality because it's shaded, right? You see it's all shaded under here? This is shaded. Remember when you graphed inequalities in math? You would put a dashed line or a whole line, and then you'd shade one side of the actual line. Sam?
I feel like this seems like an being less than or equal to 6,000.
Yes, this is your constraint, less than or equal to 2,400. If you look at that equation, go back to that equation, please. I'm going to pause. We're looking at the other corner. Yeah, but that was good. That's the intuition you wanted there. It's 480. This is the first one. This is the second one. So this solid blue line is your time constraint. And what did it say? It should be less than or equal to 2,400. So when you shade, you're shading below the line. If you didn't know to shade below the line, to test, you pick a point below the line and a point above. If it's true, when you plug it into the inequality, you shade that side. So if I pick this point right here, 50, 50, plug it into constraint. 50 times 5 plus 50 times 15. Is that less than or equal to 2,400? It absolutely is. Therefore, you shade this side of the line here. This is a graphical representation of optimization with a simple example because we only have two variables, right? The minute we have a third decision variable, it becomes a three-dimensional, what's called contour plot. The minute you have a fourth decision variable, you can't graph it. Okay, it's impossible to actually graph at that point. So this is just the very beginning idea or picture of what we're going to do with this project. And that's good. Why are these acting as boundaries? Why are the horizontal and vertical axes, I should use those terms instead of x and y. Why do they act as boundaries?
Because it can't be negative.
Non-negative constraint, right? Now over here, would one of the numbers be negative? x1 would be negative over here, and what would be negative down here? x2 would be negative down here. So these three quadrants are not included. So we have what looks like here a polygon. Now, on the next page in your reading, what did it tell you about? When you're looking for the best solution, what do you look for? Corner points. There's something called the corner point theorem, actually, that actually proves that the corner points are where you can get your maximum or your minimum values always. So in this case, how many corner points do we have? Three. One of them clearly gives me what? If I produce 0 and 0, do I get any profit?
No.
So doesn't this do what? What does this do?
Nothing.
It gives me the what? Profit. Fill in the blank.
Baseline.
Zero.
Minimum. Minimum. Baseline, 0, minimum, really. This is the minimum point, actually. But what do we want?
Actually, if you
We
burn
want
mine,
maximum.
that's the minimum.
We want the maximum. So we test the other two corner points now, or vertices. And that's on the next slide where you're going to see here. So we test the corner points. It looks like the 480, 0 corner point gives you the most profit, which tells you what Koenig was complaining about. He said, oh, nobody makes any fancy ones. What if I want a fancy one? I told him, go to another company. He's claiming this company doesn't care about fancy ones, based on this analysis. Okay, so these are your corner points here, and your goal, again, is to maximize. That's the objective function right there. Questions so far? I'm going to stop and go to Excel to use this as an example because it's very simple. Because then we're going to do ones with like 5, 6, 7 decision variables and allow Excel to help us solve it. Okay? So I'm going to pause at this point. We're going to go to Excel, but I want this. Here's our optimal solution. Here's our optimal solution, $7,200 profit. Let's go to the next constraint now that we used Excel to see this. Okay? I'm going to skip these questions. We already talked about it a lot. Hey, by the way, remember my first statement? In the very beginning, read it. Wow. Fancy is not 3 times as profitable, and it takes 3 times as much time. So we knew right away that it's got to be all sporty. That was the whole idea here. This is the reason why you could have seen this without even using Solver. Okay? All right, so let's add a new constraint. The new constraint we have is a limited supply of trucks. We're only allowed to get 2,800 trucks per month, which means 700 trucks every week. And each board requires 2 trucks. So we take a look at our inequality here. We see that it takes 2 trucks for a sporty times the number of sporties, plus 2 trucks for a fancy times the number of fancies. And that has to be less than 700 trucks.
This makes it way more complicated.
Okay, now you have another inequality, a completely different inequality or another constraint. So take a look at our new analysis here. We have this added constraint of 2x1 plus 2x2 less than or equal to 700. Again, 2 trucks for the first one, 2 trucks for every fancy one, meaning less than the total amount available of 700. Take a look at this new constraint now. It's in purple. Look at the purple constraint. That limits my feasible solution range now big time. Where was the solution last time? What was the answer again? Who knows? What was it? It was 480. It was right here. Is that in the feasible region anymore? No, it's not. So the feasible region has to be less than this inequality, but less than this one also. To be less than this one, it can't be in this little triangular region on the right. Again, this little triangular region here is no longer part of the feasible solution because this is the truck, the amount of wheels and trucks that go on there, limitation has to be less than. So we have 1, 2, 3, 4. Do I need to test 0, 0? No, I don't have to test 0, 0. Okay? But you do have to test this region. We did it last time. You probably have it already. This point and this point are new points. Test them also. If we test them and we take a look, we see now that we have a new answer. 285 sporty and 65 fancy. Okay, that is our optimal solution. Can we jump to Excel now and add this constraint in? Okay, it's pretty simple. Okay, let's add the constraint into Excel. So it's going to be 2x1 plus 2x2